these techniques. I'm going to tell you these techniques actually fall under nonlinear models. Let me tell you this. The data scientists, the machine learning experts took advantage of advancement in technology, okay, but the facts remain, they still use some fundamental principle of statistics, okay? They still use some fundamental principle of statistics, okay? They actually use some stuff, from statistics, some basic idea in statistics, they capitalize on the fact that statistical models struggle when they come to big data. So which I acknowledge as a statistician. Okay, so that's why I call myself an hybrid statistician. Hybrid statistician. That's myself. That's what I call myself. Hybrid statistician. Hybrid statistician in the sense that I did not only know the method in statistics, but I also know some algorithms because I don't want a situation whereby I was given big data and my method struggle with that and I cannot help my clients. So that's the essence. Okay, so we want to go into other variants of nonlinear models called regression trees and random forest. So let me start with the regression trees. Of course, I said that when the relationship is kind of complicated, of course, we're basically going to use a nonlinear function. Let me tell you this: the most important thing in statistical analysis is getting the appropriate mean function. If you're working with a wrong mean function, most of your assumptions will be violated. Okay, and that is the reason why we got to make sure we figure out what the mean function is basically going to be. Now, when I talk about regression trees, I'm talking about the one for prediction, because we also have a regression trees that we use for classification. Okay, but this one I'm talking about, using regression trees for prediction. And at this time around, I'm going to go into sports. For example, suppose we have a data set that contains the predictor variables, years played, and average home runs, along with the response variable, maybe yearly salary, for 100 of professional baseball players. Oh my God, I miss baseball. I'm going to go one day to watch baseball again. I remember, like something failure around Minneapolis. So I enjoy watching that game. Now, decision tree is going to look like this. What is it trying to say? When you take a look at what we got two predictor variables that we're basically trying to use to predict the response. But it's the one at the top here is years, followed by the home run, so which means using the variable importance, years actually is more important than the home runs. And that is why you are seeing that first. Okay? Of course, I'm actually going to go walk you through ways to have, the way we can actually construct this particular tree from data. Of course, next week, the arrow code for this will be included. That is part of what you're going to do in the lab. Okay, so what is the meaning of this? I know there's something I want you to take note now. Uh, this is less than 4.5, right? If I want to consider this less than 4.5, then I'm trying to talk about this side that probably players with less than 4.5 experience is expected to have the salary. If I want to go by the way of this side, I'm no longer talking about less than 4.5. I'm actually talking about exactly 4.5 or greater than 4.5. Do you understand that now in the tree? Okay, now coming back here now, players that have less, more than or equal to 4.5 experience, with, if I want to talk about this guy, I'm going to say with home run less, with home run. If you take a look at what I have this side, okay, I'm going to read this with this. Now I'm going to read this with that, okay? And you know what this guy actually means? more, more, more than 4.5, more than this home run, we have more salary. That really makes sense, of course. You have more experience, and not only that, you're doing more home runs. Of course, you're going to have more salary. So, but when you take a look at this guy, of course, more than that, but less of that we have. So, and that is why I have this interpretation. Okay, I said the player with less than 4.5 play have a predicted salary, which is the other side. The player with greater than, you're basically going to see that at the other side, I have greater or equal to 4.5, greater or equal to 4.5, except that in one that is less than and the other one that is greater than. Any question on that? Easy, right? Any question? Decision tree, that is the way it works. Okay, now, like I said, variable importance is very, very needed here to be able to know the predator we're actually going to start with. We don't just start with any. Now, if I want to make a prediction using this regression trees now, okay, we can then use this model, okay, to predict the salary of a new player. For example, suppose a given player has played 8 years. Of course, 8 years would be to this side because less than 4.5 is going to be this side. So this guy is going to be around here, okay? An average home 10 runs, okay? Don't forget, less than this is this side, greater than this is this side. So I'm going to put this guy here. You see that, right? Okay, so according to our model, of course, it's basically this is going to be the salary, not this guy. The only condition on that this guy can be the salary, it has to be greater than that. Any question? That's prediction. Which regression trees? Any question? Well, let me tell you this. We have a regression tree like this. How do we get to this place? How do we actually get to this tree? Okay, so how do we get to this tree in the first place? I'm actually going to explain the procedure to you now. Okay, let's get started. Now, I need you to pay attention. I told you the other time, statistics and machine learning or data science and the like, we are actually targeting the same thing. Okay, we're targeting the same thing. Now, if I want to build, the regression models, the regression trees. Of course, I'm actually I can have like possible numbers of predators, like just like what we normally have, and a particular response. Of course, the very first thing I have to actually use my training data. But before you use your training data, you got to make sure your data is, you've already looked at your data and you've put that you've in a very good statistical standing. There's what we call data mining, where you're going to make sure there's no missing values, everything is fine. Then when the moment, which we call data preparation, okay, and don't forget you're actually going to split the final data set you're going to use into two groups, right? The training and the test set, where a good numbers of data set we go for the training, 70-30 or 80-20. Okay, now when you do that, we're not going to use, in the first step here, we're not going to use all the predators. In fact, we have a rule. Now, this is what we're looking for. Consider all predator value x1 to sp, and there's going to be possible values of a cut point. Don't forget the other time, that was a cut point less than, greater than something, right? Okay, cut point for each of the predator. For each of the predator, okay, they will not only have one cut point, they will have a lot of cut points. Okay, then we need to choose the predator and the cut point such that the resulting tree, the tree that we're going to, because there's going to be a lot of trees. Okay, but we actually want to choose a tree that will have the lowest residual standard error. In a situation where I'm actually looking at a classification problem, I'm not going to use the residual standard error, but I'm going to use a misclassification error. Let me write that down. Misclassification. Misclassification error. So we use misclassification error to decide when your response variable is categorical. Does that make sense? Where you are classifying. Okay? Okay. Now, after that, in the step 2, you apply cause of complexity pruning to the large tree to obtain a sequence of bare trees as a function of alpha. Let me tell you this. This is very similar to shrinkage in a lasso regression, where we basically want to prune some some unimportant predictor variable to 0, so that our model will not be noisy. Because if our model is noisy, you know what's going to happen, right? High variance. The way you have high variance, your prediction is going to be low. Like, okay, now, and we don't want a situation where, the tree that we have, okay, will be complex. And that is why we actually, in addition to minimizing, using the RSS, there's also going to be a penalty. Okay, and that was why I said for each possible tree with the terminal nodes, of course, every tree, we have a terminal node. Okay, find the tree that minimizes the RSS, not only RSS plus this guy, and you have to put into consideration, know that as we increase the value of alpha, trees with more terminal node are penalized. Because somebody may want to say, oh, I maybe when I have so many terminal nodes, that's going to do a great job, but you're going to have a lot of stuff. You're going to make it noisy. We don't want to make it noisy, okay? And that's ensure that the tree doesn't become too complex. Now, what is the next thing? We use a code full cross validation to choose alpha. Okay, because we're going to have so many values of alpha. You get what I mean, right? Once we found the best tree, because you need to first find best tree for each alpha, right? Which means there's going to be more than one alpha, right? Okay, then we can apply k-fold cross validation to choose the value of alpha that minimizes the test error. Oh my God, test error. What do I mean by that? It means right now I'm on the test data. I'm on the test data. Okay? So now, which we call the test error. And after that, we're going to choose the final model. We choose the final model to be the one that corresponds to the choosing value of alpha. What choosing value of alpha? The choosing value of alpha that corresponds to the lowest test error. Any question? Okay. Now, the moment we do that, we should be fine. Now, these are the pros and cons of CAT models. Very easy to interpret. You can see now some parts of this approach, it is statistical to me, even though this is in machine learning. It's statistical to me because there's a lot of transparency. There's a lot of transparency, and because of that, they will be easy to interpret, very easy to explain, very easy to visualize, and they can also be applied to both regression and classification problem. The one I just explained to you now is when the response variable is continuous, not when it is categorical. Okay, but except that we have disadvantage. They tend not to have as much as predictive accuracy as other nonlinear machine learning algorithms. However, by aggregating many decision trees with methods like bagging, boosting, and random forest, we actually achieve greater accuracy. And let me tell you this. I told you the other time, the machine learning expert took advantage of advancement in technology. Not only that, they also understand some stuff we're doing in statistics for them to be able to get an approach that will be better than this in the name of random forest. Then they go by way of bootstrapping. Of course, I walk you through bootstrapping the other time. You have a sample of data. We can actually generate different versions of that. They hide under that. And not only that, different versions of that on each uh, subsample they choose. They get this decision tree on each of that. And they still go back again and borrow another knowledge from statistics using the power of average. So what they are doing in machine learning is statistical as well. Highly statistical. Okay. Now, because of that, I'm going to go into random forest now. It's also class of nonlinear models. And of course, you know, the reason why we want to consider random forest is because the decision tree we use may suffer from high variance. Okay? And how do we know? When we split our data set into two halves and you actually apply decision tree, you're basically going to have different results. Oh, this is looking very close to the reason why Francis reparameterized von Bartalaffi in 1988, because of the fact that the parameters, the estimate of the parameter using age to length data is different from when you use a tagging data. Look at that. Okay, so let's go to the procedure now for random forest. Take B bootstrap samples from the original data set. In this class, I've already walked you through bootstrapping, right? If you have if you have 200 in the sample, you can produce several versions of that. Okay, it's going to be that same 200, only that different version, right? Then build a decision tree, okay, on each bootstrap sample, okay? But we have an approach. There's something that I want you to understand. If you take a look at this, build a decision tree for each bootstrap sample. When building the tree, each time a split is considered, only a random sample of M predator is considered as split candidate. You don't use sub predators. But you are not going to be the one that will decide. Is basically going to choose that randomly. But you know what? If you're working, if the response variable is continuous, then you're going to use the square root of P. Right? So, you're going to use this for classification. And for continuous, you're going to use P divided by 3. Okay? P divided by 3 for regression. Okay? For classification, you use square root of P. Please take notes. For P, P over 3 for regression, square root of P for classification. Okay. Now, average prediction. Look at the average. Power of average. They took advantage. Okay? They borrowed that from stat. That's working. Because mean has power. So average the prediction of each tree to come up with a final model. And it turns out that the random forests tend to produce much more accurate model compared to single trees. But let me tell you this. Why is it called random forest? Random because of the way you generate your bootstrap. That is why it's random, Okay, now I'm going to walk you through, I provided an arrow code for the random forest here on a particular data set. Okay, you need to load a package random forest if you really want to actually, use this on your data. Okay, step 2, the data you are working with. Here we actually working on hair quality. Okay, which contain hair quality measurement in New York on 153 individuals days. Now, this is the structure of the data. Take a look at that. And when you have your data set, you don't go ahead fitting model, any kind of model at all. You actually need to prepare your data for analysis If you write this code, sum, if you really want to know, you want to find numbers of row with missing values. Sum, this complete dot cases air quality. This is the name of the data. You've already imported the data. Oh, this tell you, 42 missing values. How do I take care of that? There are some researchers that will say, okay, I'm actually going to delete the rows or delete. You can't delete the column. The column is the predator. And if you're deleting the row, which means you are not only deleting the missing value, you're also deleting some other values. And that is the reason why some said, okay, just replace them with the median. Look at that. This code is for that. Okay, replace not available like missing value with column medians. Not the median of uh, the column that contain the missing value. You get the median of that. Then you put that value to replace what is missing. Okay, that is the essence of. Oh, go ahead.
Is there a thought about like putting the median versus like the mean?
Or instead of median mean, right? It depends. Uh, Most of the time, for the case of the missing, because why we don't want to put the median? What if there's an outlier? You know, me may not be a good representative. Like something is missing, and I really want to make a projection of what that value is going to be. Median will make more sense. Yeah, that's a good question. Okay, right.
Like on that same topic, would it be like to wait, like anchor it down? So like if you were to switch the median, then the mean would turn into the median.
Uh,
I guess that right?
uh, you know, when you talk about replacing stuff, you look at the distribution,
Yeah.
and the moment is you can find data, a point that is not consistent. If you put the mean,
Yeah.
it's basically not going to be a good estimate because we have already proved that statistics, just like what I did today when I was presenting the results. I faced a situation where I needed to choose between using the median and the mean, and I realized, there's something in statistics. What determines using the mean and using the median depends on the probability distribution of the data set. So most of the time, because we know there's going to be kind of a skewness in that data. So we actually going to put the median instead of the mean. Yeah, it should be advisable to put the median. Because you know why? Median is not sensitive to outliers because it's always going to be in the middle. Okay, now the next thing now is building a random forest. I will advise, like if I want to set this question in exam, I'm actually going to suggest the value you're going to set in your seed. Don't forget, when you want to split your data into training and test set, um, if you don't set a seed, what will be your training data will be different from what will be my training data. You are simulating them randomly. You get what I mean, right? I'm actually going to have a uniform set of data in both the training and the test. I'm actually going to say, okay, use this value in the set of seed. I'm likely going to say use 5302, which is the cost code. Okay, so the next thing now, I'm going to feed the model. Okay, now of course, looking at this now, anytime you see or using this dot points means we've considered or predator because what if you have 15,000 of them, that you're now going to write this plus that plus now that's going to take forever. So then we have this. What this is trying to display is that we're basically going to use 500 trees. Okay, the numbers of trees you're going to use depend on the data. Okay, we put that and this what we have, and the number of variable try at each split is basically 1 without mean square error. Okay, so after that, here we want to find the numbers of trees that produce the lowest test MSC. It is not going to be all the trees that was suggested initially. How many of them? 82. And how do you think we know? We actually know. We look at the, if you look at it, we're using mean square error. Mean square error. Okay, then we can find the root mean square error of the best, okay, of that best model. Let me tell you what is the difference between the mean square error and the root mean square error. It is the same difference between the variance and the standard deviation. If how do I tell about the reliability of the mean, right? If I compute the variance, I can use variance. The variance and the mean, they are not in the same unit. The variance is in the square unit. Okay? I need to use a metric of evaluation that will have the same unit with the mean. And that was why finding the square root of the variance, the standard deviation and the mean, they basically have the same unit. Just like what I'm doing here, square root of the mean square error. So here I said from the output we can see that the module that produces the module that produces the lowest test mean square error. When I say test mean square error, means I've now used the test data. Okay, use 82 trees. And we can also see that the root mean square error for that module was that. Okay, we can think of this as the average difference between the predicted value of ozone and the actual values. Of course, we have put that into consideration. If you're talking about getting the root mean square error, you're focusing on the difference between the observed and the predicted. Okay? Now, I talked about variable importance the other time. Okay? What is it telling us? Oh, wind. Wind is the most important, followed by temperature and so on like that. These are the predictor use. With that, you can just write var in plot model. You're basically going to have that. Of course, I know here that the variable that will be on the top is basically going to be wind. Okay? Take a look at that. Now, the next thing you turn the model, okay, and you turn the module. I think I gave some minutes of that. This is going to give you the idea of the numbers of predictor use. And it's telling you have to use the numbers of predictor where the out of bag error is minimal. And here it is 2, right? And it is 2. Okay. If it is 2, then it corresponds to this because we have 6 numbers of predictors. What is 6 divided by 3? That would be 2. Look at that. So this actually confirmed that. The out of bag estimate of the error, this is where it is the smallest, which is at 2. Okay? Now, then the next we can make a prediction using the resulting model. In case we know the values for each of the predictor, we can actually make a prediction with that. We're done. Now, let me tell you what we're going to do next week. Somebody contacted me during my office hour yesterday, and I told the person, the appropriate regression needed for a project is basically is here. Now, let me tell you what I want to do on Monday, next week, since I still have time. Next week, what we actually going to talk about what type of regression model can be used when the response variable is categorical. Okay, it is binomial regression model that we call logistic regression model. Okay, what of in a situation where the response variable is a count. I'm talking about if the response variable is the number of visitors or number of customers that visits a restaurant, and I have some predictor variable. Okay, that's a count data. That's not continuous. The type of regression you're going to use there is going to be a Poisson regression. What actually determines the functional form of a model most of the time rely on the nature of the response variable. You don't talk about linear regression when the response variable is a count, or where the response variable is categorical. You don't talk about using linear regression. Now, what of in a situation whereby your response variable is a decimal, like something that lies between 0 and 1? You're talking about percentages, rates, proportions. Then we're going to use beta regression. Beta regression. When you use a linear regression model, oh my God, or logistic regression model, you're basically going to mislead. In fact, there's going to be violation of everything, all the assumptions. Your assumption get violated because you are using inappropriate functional form. That's why you have a lot of violations. Okay, so beta regression is used when the response variable is a rate, proportion, percentages. That is why you use beta regression. I'm going to walk you through that next week. Now, the next one is what we call the instrumental variable regression. Oh my God, I love instrumental variable regression. You know why? For instance, I want to look at the effects of return, the amount you spend on education. You are looking at that effect on the salary. If you fit a model, if you fit a simple linear regression model, there's going to be a violation of